Last time, we learned about the spherical wrist as a way to turn the standard 3 degree of freedom manipulators into 6 degree of freedom manipulators. In this video, I'm going to show you an example of finding the rotation matrix all the way from the base frame to the end effector frame for a complete 6 degree of freedom manipulator. As your manipulator gets more degrees of freedom, the likelihood that you will make a mistake while finding the rotation matrix increases. Because of this, after I show you this example of a 6 degree of freedom manipulator rotation matrix, we'll spend some time talking about how you can check your own work and find out if the rotation matrix you've derived is correct or not. Here's the kinematic diagram for the example we're going to be doing today. This diagram consists of a spherical manipulator here, and then we have a spherical wrist attached to the end. In order to find the rotation matrix, I need to have frames drawn on my manipulator, but I don't necessarily need to have the links labeled. So I'm going to start by labeling the frames on this manipulator. For the base frame, the z-axis has to be the axis of rotation, but the x and y axes are a free choice. With the next joint, again, the z-axis has to be the axis of rotation. Now, when I draw the x-axis in, I need to make sure that x1 is perpendicular to both z1 and z0. And I also have to draw x1 so that it will intersect z0 if that is at all possible. So if I made x1 go up or down, it would satisfy the requirement that x has to be perpendicular to both z1 and z0, but x1 would not intersect z0. For that reason, I'm going to draw x1 going off to the right. This way, if I would draw x1 back, it would intersect with z0. By making x1 go right or left, I can satisfy both rules at the same time. Now I find the y direction by the right-hand rule. Next, for this prismatic joint, z has to be the direction of motion. Now, x can be either up and down or into and out of the page. But whether I draw them up and down or into and out of the page, x2 will not intersect z1. Because of that, I have to move the location of the center of frame 2. I'm going to move it back to here. So I'll draw this frame in purple to try and keep it separate from frame 1. Here's z2. Now, x2 is going to go up because that way it will be perpendicular to both z2 and z1. And also, x2 will intersect z1. That leaves the frame y2 coming out of the page towards me. Next, for frame 3, z3 has to be the axis of rotation. If I make x3 point up or down, it will intersect z2. Also, if I make x3 go into the page or out of the page, it will also intersect z2. So in this case, we can choose x3 to be either into or out of the page or up or down. To try and simplify the calculations, I'm going to make x3 point up because that will make it be in the same direction as x2 and will end up simplifying our calculations later on. This leaves y3 pointing out of the page towards us. I'm also going to erase this red z2 in order to try and clean up the picture a little. Remember that the actual z2 is shown back here in purple. Now for the 4 frame, I'm going to make z4 come out of the page. I could make it out of the page or into the page because it has to be the axis of rotation. Now, in order to make x4 be perpendicular to both z4 and z3, I could make it either up or down. I'm going to choose to make it up because, again, that will make it the same as x3 and will end up simplifying our math a little bit. So that leaves y4 pointing to the left. That's y4 right there. Now, z5 is the axis of rotation. I could make x5 be either up or down in order to make it perpendicular to both z5 and z4. However, if I do that, x5 will not intersect z4. And so I have to move the center of the frame 5. And I'll move it back to the center of frame 4, and I'll draw it in purple. So z5 is going to the right, and then I'm going to make x5 point up so that it is perpendicular to both z5 and z4, and also intersects with the axis z4. That leaves y5 pointing out towards me. Lastly, I have to draw a frame on the end effector. If possible, I want to copy frame 5. That would make z6 point to the right, x6 point up, and y6 coming out towards me. I have to make sure that if I copy frame 5 as frame 6, that this still follows the 4 rules that are required. So I have to make sure that x6 intersects both z5 and z6 and is perpendicular to both z5 and z6. And it does, so we're good to go here. I'm going to erase the red z5 in order to clean up the picture a little bit. And here we have all of our frames drawn on this 6 degree of freedom manipulator. Now, I want to find the rotation matrix that goes all the way from the base frame to the end effector frame. I know that I can do that by finding each individual rotation matrix. From 0 to 1, from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and multiplying them together as shown here. These are all dot products taken between all of these 6 individual matrices. Let's start with R01. R01 is a rotational axis. That is a revolute axis. And so one part of the rotation is a rotation of theta 1 around the original z-axis. So in my rotation matrix, I start by getting the standard form of a rotation around z, and I plug in theta 1. Here, I'm going to abbreviate cosine just with the letter C, and I'm going to abbreviate sine with the letter S. Now, I'm not finished with this rotation matrix yet. I still need to represent the rotation of frame 1 relative to frame 0 as it is in the kinematic diagram. The kinematic diagram always shows what the manipulator looks like when all of the joints are in their 0 degree position. I'm going to use the shortcut method to do this. In the shortcut method, I look at the frame I'm going to, in this case frame 1, and I look at the projection of each of these axes on the frame that I'm coming from, in this case frame 0. x1 is in the same direction as x0. In other words, the projection of x1 on x0 is 1. And the projection of x1 on y0 and z0 are 0. y1 is in the same direction as z0. In other words, the projection of y1 on z0 is 1. So I fill in the position in the rotation matrix that represents the projection of y1 on z0 with 1. And I fill in 0 in the positions that represent the projection of y1 on x0 and y0. z1 is in the opposite direction as y0. And so I get a -1 in the position that shows the projection of z1 on y0, and the other two positions are filled in with zeros. I can either multiply these by hand, or I could put them into my code right away. I'm going to multiply these by hand here, and the result is what I'll put into my code. Now, I'm going to try not to make any mistakes as I go, but if I do make mistakes, it will come out later on when I test the code, when I test my matrices in the code. So for now, I'm going to assume that I have this right, set it aside, and move on. Next, let's do R12. R12 is also a revolute joint, and so we have a rotation of θ2 around Z. Next, we also need a matrix that tells us how frame 2 is rotated relative to frame 1 in the kinematic diagram. x2 is in the same direction as y1. y2 is in the same direction as z1. And z2 is in the same direction as x1. Again, I'm going to multiply these by hand now, and I'll put the result into my code. I'm going to set aside the rotation matrix 1, 2, and move on to the rotation matrix 2, 3. This joint is a prismatic joint, so I don't have a rotation part of this rotation matrix. The only thing I have to include is the part of the matrix that tells me how frame 3 is oriented relative to frame 2 right now in the kinematic diagram. Frame 3 is in the exact same orientation as frame 2. In other words, x3 is in the same direction as x2. y3 is in the same direction as y2. And z3 is in the same direction as z2. You see that what we get here when we have no rotation is the identity matrix. The identity matrix is the matrix that means no rotation. I'm now going to take R23 and set it aside. Now, moving on to R34. This joint is a revolute joint, and so we have a rotation θ. I'm going to call this θ4, even though we don't have a θ3. The subscript on the theta's indicate which frame is affected by that rotation. Since the rotation θ4 mostly affects the 4 frame, that's why I'm going to call it θ4. I start with the rotation that is the standard rotation around Z, and I'll plug in θ4. Next, I need the part of the matrix that tells me how frame 4 is oriented relative to frame 3. x4 is pointing up. That's the same direction as x3. So x4 and x3 are in the same direction. y4 is pointing to the left. That's the opposite direction as z3. In other words, the projection of y4 on z3 is -1, and the projection on x3 and y3 are 0. z4 is coming out of the page, and that's the same direction as y3. So I get a 1 in the position that shows the projection of z4 on y3, and 0 in the other two positions. I multiply these together by hand. Then I'll set R34 aside. and move on to R45. R45 also has a rotational part because we're dealing with a revolute joint. We have a rotation theta 5 around Z4. So we start with the rotation matrix around Z. And then we fill in the part of the matrix that tells us how frame 5 is oriented relative to frame 4. Z5, X5 is pointing up. That's the same direction as X4. Y5 is coming out of the page. That's the same direction as Z4. And Z5 is pointing to the right. That's the opposite direction as Y4. I multiply these together and then I'll set it aside. Next, R56. Here we also have a revolute joint. We have a rotation of theta 6 around the Z-axis. Then we need the part of the matrix that tells us how frame 6 is oriented relative to frame 5. But, as is often the case between the end effector and the frame immediately before it, we have no rotation matrix here, because frame 6 is in the exact same orientation as frame 5. Anytime you multiply a matrix by the identity matrix, the matrix won't change. So I can skip the part here where I write out the rotation matrix, that means no rotation, and then multiply by it, since I know that it will not end up changing this matrix at all. I'm going to take this R56 matrix and set it aside. The next step is to multiply all of these matrices together. It's possible to do this by hand, but practically we would probably stop here and put the matrices into our code. So now I'm going to switch over to our Python code and we're going to write some code to multiply these matrices together. Another benefit of doing this in the code is that we can then test to find out if our matrices are correct or not. Let's go and switch over to our Python code now. Here I have some simple code to multiply matrices together, similar to what we developed in the last videos. I've imported numpys, np, and then I've entered two angles, T1 that stands for theta 1 and T2 standing for theta 2. I want these to be in units of degrees, so we then convert the two angles to radians. We can then use them in our rotation matrices. I'm now going to expand this code in order to deal with 6 rotation matrices and multiply them all together. And then we'll take a look at how we can test this to find out if the matrices that we developed are correct. The first thing I'm going to do is copy these two angles and paste them. I'm going to allow for as many as 6 angles. In our example, we only have 5 angles, and that's okay. We'll build this code to allow for as many as 6. All I'm going to do is renumber these to be T1, T2, T3, T4, T5, and T6. I'll need to convert all of them to radians. Next, I want to enter all of the rotation matrices that we just derived a moment ago. Just like there's a good chance that I made a mistake in deriving the rotation matrices, there's also a good chance that we can accidentally enter these matrices incorrectly. That's one of the reasons why it's so important for us to test the code. It looks like my R01 and R12 are already entered according to what we just derived, but now we need to add in the other matrices. we need a matrix R23, R34, R45, and R56. R23 is the easiest one. That was the identity matrix. I'm going to pause the video while I type this in, and you should do the same. Pause the video and try to type in the matrix that you derived. Okay, now we'll do the same with R34. I also noticed that I made a mistake in R12, so I went back and tried to fix that. Make sure that you're changing the variable here also. R34 should take as its input T4, whereas R12 should take as its input T2, and R01 should take as input T1. Do the same for R45 and R56. Change the matrices so that they agree with what you derived previously. As I was typing in the matrix for R45, I noticed that I made a mistake in the derivation, putting theta 4 in this matrix instead of theta 5. If you notice these kinds of mistakes as you're typing in the code here, go ahead and fix them now. We will probably discover more mistakes as we test the code in a moment. Okay, once you have all 6 of these matrices typed in, we're going to do the dot product, multiplying these matrices together. In Python, the command np.dot can only take 2 matrices at once. So we're going to have to multiply all these matrices together piecewise. First, we'll get R02. Next, we'll get R24. By multiplying together R23 times R34. Then we'll get the matrix R46 by multiplying together R45 by matrix R56. Then we can get the matrix R04 by doing the dot product of R02 and R24. Finally, we can get R06 by multiplying together R04 times R46. Now, here we have one print statement. In order to test this and find any mistakes that we've made, we want to print out all of the individual matrices as well as R06. If we just print out all of these matrices in a row, it will be hard to tell what's what. So I'm going to start out with a print statement that says /n, that is, put a blank line or a carriage return, and then we'll write out R01 equals. And then what we want to print here is R01. Now we'll copy these 2 lines, and we also want to look at R12. And then we'll print R12. We want to do this for each of the matrices that we've calculated. 2, 3, 3, 4, 4, 5, 5, 6, and then finally R06. Okay, now let's run the code and see if we have any errors. When I run my code, I get an error that says value error, shapes 3,3 and 2,3 not aligned. The error is in this line of code where we calculate R02. This tells me that I probably made a mistake in typing in R01 or R12 in such a way that one of these two matrices does not have 3 rows and 3 columns. So I'm going to go back in my code and see if I can find the source of that error. Here I see that when I was typing in R12, I only gave it 2 rows. R12 needs to have 3 rows. So I'm going to try and fix this error by adding in the 3rd row. Then I'll try running it again. This time I get no errors. The fact that I get no errors doesn't mean that my calculations are correct, it just means that I've typed it in sufficiently well. So now we're going to try and find out whether we derived our equations correctly. In order to do this, the first thing we want to do is set all of the angles theta to 0. Now, when we look at our output, we can compare this output to the kinematic diagram to see if it looks correct. I'm going to try and put this output next to the kinematic diagram to show you what I mean. I'll scroll up to R01. Remember that the kinematic diagram shows us what the manipulator looks like when all of the angles are 0. So since we set all of the angles to 0, this rotation matrix R01 should be telling me how frame 1 is currently oriented relative to frame 0. This rotation matrix is telling me that x1, represented by the first column, is in the same direction as x0, represented by the first row. I want to look at my kinematic diagram and verify that that's true, and I see that it is. The second column of R01 is telling me that y1 is in the same direction as z0. I need to look at my diagram and make sure that that's true here also. Finally, the matrix tells me that z1, represented by the third column, is in the same direction, or the opposite direction rather, as y0, represented by the second row. In my kinematic diagram, I see that z1 is coming out of the page, while y0 is pointing into the page, so it looks like this matrix is correct. I'm going to go ahead and do the same thing with each of the other matrices. So R12 tells me how frame 2 is currently, that is in the kinematic diagram, oriented relative to frame 1. I want to check and make sure that this is correct. Is x1, or x2 rather, in the same direction as y1? It is. The second column says that y2 is in the same direction as z1. That's also true in my kinematic diagram. And z2, it says, is in the same direction as x1. That's also true in my kinematic diagram. I'm going to go through each of these other matrices and make sure that the matrix agrees with the frames that I see in my kinematic diagram. Pause the video for a moment and check each of your matrices to see if this is true. Once we've checked each of the individual rotation matrices with the kinematic diagram, we also want to check the rotation matrix 06. 06 is telling us how the 6 frame is rotated relative to the 0 frame. In my example, R06 is telling me that x6 is in the same direction as z0, which is true in the diagram. y6, the second column, is in the opposite direction as y0, the second row. That's also true. And Z6, the third column, is in the same direction as X0, the first row. That's also true in the diagram. So far, our derivations check out. However, only testing your matrices against the angles all being 0 sometimes will miss errors that you've actually made. Here's another test that we should do. We could set each angle, theta, equal to 90 degrees, one at a time, and then look at the matrices. I'm going to set theta 1 equal to 90 and then run the code again. These matrices are telling us the orientation of the frames relative to each other if theta 1 has rotated 90 degrees. You have to do a little bit of imagining in your head what this will look like in order to test if this is true. Can you imagine what the frames would look like if theta 1 was 90 degrees? If theta 1 was 90 degrees, x1 would be pointing into the page the same direction as y0. We want to make sure that our matrices say that that's true in our output. Now that our angles are not all 0, the numbers are less nice. But if I expand this screen a little bit here, you can see that some of these numbers, which look large and crazy, are actually either 0 or 1. This first number, 6.123, etc., is raised to the power of -17. So this number is actually 0. This first R01 matrix is telling me that my x1 axis is in the same direction as y0. If we would rotate theta 1 90 degrees, that would be true. x1 would be pointing into the page in the same direction as y0. Similarly, y1 would be still pointing in the same direction as z0, and that's what my matrix says as well. Z1 would be pointing to the right, the same direction as x0, and I see that my matrix confirms that case also. Another way to test this is to always look down at the output R06. We can imagine how the 6 frame would be rotated relative to frame 0 if theta 1 was 90. If that were the case, Z6 would be pointing into the page, the same direction as Y0. So we can look at our R06 matrix to see if Z6 is in the same direction as Y0, and we see that it is. You can check your derivation more thoroughly by setting each angle to 90 degrees by itself and then imagining in your head what the frames would look like in that case, and then check to see if the matrices agree with you. If your matrices look correct in the case where all of the angles are 0, and it also looks correct in the case where only one theta value is 90 at a time, then you're probably correct. In the quiz for today, I'm going to give you another kinematic diagram and ask you to find the rotation matrix R06. It's a good idea to go ahead and test your results after you find the answer in this way before you type in the final answer. Even after many years of practice finding the rotation matrices, it's very easy to make a mistake, and it's good practice to always test yourself before you commit to your final answer.